will take a slightly more deep look at multi-qubit gates. Last lecture we already met CNOT, control not gate, so which is like a standard gate in all quantum computing papers. You take any quantum computing paper, you will have a lot of diagrams with this symbol. Okay, C0 or Cx gate. So this is the action of this C0 gate. So it has target and control qubit. It applies X to target when control is 1. So this is actually very nice notation. Once you understand what it means, you can easily read quantum circuit diagrams even with more complicated notation. This dot just controls application of this qubit. Okay, so when we use this C0 in any, and we want to write formula, it's not very often because it's much easier to use some quantum simulators to calculate what a particular sequence of gate does. But sometimes we want to write a formula. So it's important to write to which qubit we apply this gate. With control gate, not just with control X gate, but with any type of control gate, the first qubit that we indicate, so the one that stays near the gate symbol, is the control symbol. So here 1, here is control 1. Second is the qubit to which we apply gate. So this is like a general rule. No matter whether we are talking about control X, control Z, or some other gates that we can use. Okay, so let's just consider a few very simple circuits with C0. So suppose we have this simple program. We start with 0, 0, as always. We have usual NOT gate, and then we have control NOT gate. What will be the final state of the system when I measure it here? So what will be the final state? Louder, please.
1, 1.
Yes, the state will be 1, 1, so it's very easy. In the cases when we have just X gate and control X gate, so this is a gate which also exists in classical walls. So in classical logic, this is just NOT, this is control NOT, so it is very easy to understand what this gate do. Here I have 0, 0, I flipped a qubit number 0, so I have 1, or I will count qubits as we write them in Qiskit or Kir, so 0, 0. Here I have 0, 1, and this qubit is flipped, so output is 1, 1. Okay, and what if I have circuit like this? So this one is a little bit more complicated because here I have Hadamard gate, and Hadamard gate is a gate that does not exist in classical logic because it puts qubit in superposition state. This is not something that we can do classically, so anytime we see Hadamard gate, we know, okay, this is something quantum. This is some quantum stuff. We cannot just write logical formula like that. So what will be the output state in this?
Complement between 1 and minus X.
Are you sure?
No.
Okay, so let's work it out. So here I have state 0, 0. Here I apply Hadamard gate to qubit 1 and X gate to qubit 0. So I start with 0, 0. Then I apply Hadamard gate to this qubit and X gate to qubit Q0. So what is this result of this? Hadamard gate acting on state 0.
Plus?
Plus, yes, so this is plus, so this is the state, we apply Hadamard gate, and this is on a Bloch sphere in the direction of plus X. So this is state plus. Here I will have 1, because this is the usual state. Okay. So this is the state of my 2-qubit system here before application of this control NOT gate. Now, at this point, qubit Q0 is in state 1. So this X gate is activated. We apply X gate to this qubit Q1 plus. So what will be, sorry, what will be the result of application? I'm sorry. What would be the result of application of X gate to this state?
Minus.
Are you sure? So X gate is a rotation about X axis, right? Where on a Bloch sphere state plus is, where it is directed relative to X, Y, Z gates.
The x-axis.
X-axis. So I have state along X-axis and I rotate about this axis. This state does not change. Okay, there may be some phase change because like
It's inverter along z-axis.
so I start from 0. So this is z-axis, this is x-axis. I apply Hadamard gate. This is rotation about axis that goes in this direction. I apply rotation, I have state in the x direction. Now I apply X gate. So I rotate about this axis. So nothing happens to this state. Yes?
Can I also imagine it in a way that I can write plus as a superposition of 0 and 1 of equal parts, so I just apply X to both?
Yes, yes. Exactly. You can also think like this, and actually this is like a safer way to think, because here I apply X. So this X0 is 1 plus X1, which is 0. So this is the same state as before. And such, like, for me, it's more difficult than with Bloch sphere, because if you have some experience working with Bloch sphere, it's very easy. Okay, plus state is along X, so rotation does not change. So if you are more analytical thinker, that formula may be easier for you, or if you don't have a lot of experience working with Bloch sphere. So then formula is easy. And this formula is also like safer, because with Bloch sphere, again, if you don't have a lot of experience, you may make mistakes, because say state plus does not change when we rotate about x-axis, but also this is true for state minus. It does not change. But if we consider the same action on state minus is 0 minus 1. So x0 is 1, x1 is 0. So we see here I have 0 minus 1, and here I have 1 minus 0. So this state changes its sign upon application of X gate. This, when we consider like just state minus, this is global phase, it does matter, and therefore on the Bloch sphere we cannot see it. But if you don't have enough experience, you can think, okay, X plus is the same as plus, X minus is the same as minus, so then you use superposition of the states and you get the wrong result. Because this global phase, when we consider just the state minus, becomes relative phase when we consider superposition of plus and minus. Okay, but here we have this situation, so we have plus 1, and so control qubit is in state 1, so we apply X gate to this qubit, but this state plus state does not change upon application of X gate, so the result here will be the same as before CNOT gate. So this is just plus 1. Okay. Now let's consider this circuit. So here I have some unknown gate. I don't know, something here. And here I have Hadamard gate, and then there is control NOT gate. What will be the state of the control qubit, this qubit, at this point?
Plus.
Why?
Because of the previous
Yes, because of we can use the same arguments and previously. If here is 0, I don't know what is here. It can be 0, it can be 1, it can be superposition of 0 and 1. But if here is 0, then this on this state I act with Hadamard gate and nothing more, so it's state plus. If here is 1, I have Hadamard gate, X gate, but Hadamard X, while acting on 0 is the same as Hadamard gate. So this is such interesting circuit. So in which state of this target qubit is always plus, no matter what we put here, no matter what state we prepare at this point. Okay, so CNOT gate has absolutely no effect if target qubit is in plus state. So this combination is not very often used in quantum computing, but very similar is used. So if instead of just Hadamard gate, I have X gate and Hadamard gate, then here I would generate not state plus, but state minus. So control X gate does not change this state minus, but it flips its phase. So if here instead of state plus I have minus, I have X and then Hadamard gate and then control X. So what will happen? Such circuit will not change anything with this state, but it will flip that component of wave function for which at this point we have 1. So it will flip sign only of components for which this qubit, control qubit has 1. And if control qubit is 0, well, then it will do nothing. Yes?
I don't really understand this phase change for minus that doesn't happen for plus. Like the gates, they rotate the Bloch vector 180 degrees around the
x-axis, yes.
So why does the direction matter for the phase change of its p-half?
Well, because when we are using Bloch sphere, we have to think only of like this state on the Bloch sphere. It should represent the whole state, not one part of superposition. Like we cannot superimpose Bloch spheres. We cannot say that, okay, I have qubit and it's in the superposition, so this is Bloch vector for one part of superposition, this is Bloch vector for another part of superposition. This would be wrong, because when we derive this Bloch sphere for formulas, we consider two terms in the superposition of a qubit state. So to have like point on Bloch sphere is already describes the whole superposition. So when we consider, and then when we look at the Bloch sphere, and here we see this is the state minus, well, it does not, like if we have state minus and apply X gate, just the state minus, it does not change, because what changes is just its global phase. And global phase is irrelevant. So, but if you want to consider superposition of plus and minus on a Bloch sphere, it will not be like this case plus this case. You have to consider superposition of the states, and you will have state like that. And then you apply a rotation and you see that it changes. So when we are using Bloch sphere, we are talking about the whole state. We cannot use, okay, Bloch sphere argument for one part of superposition, Bloch sphere for another part of superposition, and then add them together. We will get a wrong result. Exactly because Bloch sphere does not represent, like this, like if Bloch sphere represented these global phases, that we can do this, but Bloch sphere does not represent global phases, and therefore it does not work for superposition of states. This is like the main limitation of Bloch sphere. Bloch sphere is very nice picture when we work with single qubit. Well, like you can really understand like what's going on there, like you have some experience with that, you want to put qubit into a particular state, it's much easier to do with Bloch sphere than with analytical equations. Well, it's not that difficult right now that we have computers who can do all the calculations for ourselves. But if you want to design, say, a particular gate, like one of the home homework problem. You want to design a particular gate. You have this matrix of the gate. You want to understand how to realize this gate using standard single qubit gates. Well, you can work out math, or you can understand like what type of rotations this gate describes. Like one of the homework problem, you find the eigenvector of this gate, so you know rotation axis, you know rotation angle, and then you simply make gates that does this rotation. This is like the simplest one that people can do without help of computers. So this is great for, Bloch sphere is great for single qubits. We consider each state like a full state, no superposition, that's all. But Bloch sphere cannot be used if we have more complicated cases. For example, if we have two qubits which are entangled, like in Bell state, well, we cannot represent it on a Bloch sphere. Well, we can. I will show something how we can represent it. It's not exact representation, but something I will show at today's open lecture, how to do this. Okay, so here, this is such nice nice circuit that does not change the state of this qubit no matter what we do to the control qubit. And this shows like that this C0 gate, it does not behave exactly as classical gates when we have some quantum gates in addition to this classical. Because if, like for classical C0 gate, control NOT gate, it always does something to target qubit, or if we are talking about classical gates, that would be target bit. It always flips it if here is 1. So there will always be some changes. Here we can create such state which is resistance, you can call it resistant to application of control NOT. Okay, and now what about this circuit? What will be the end state of 2 qubits if we run this circuit?
Control, it always measures from z-axis, or?
Well, control is like when it's 1, it applies x, when it's 0, so yeah, so we distinguish between state 0 and 1. So this control always works, you can say that it works in that axis.
So there will be superposition if it's x, both states together, 0 and 1.
0 and 1.
Hmm?
0 and 1.
0 and 1? Okay, let's work it out. So again, so we start from 0, 0. Then I apply Hadamard gate to qubit 0. So I have state 0 plus. And now I want to understand what control X does. So, well, when control qubit is in superposition state, so it's not possible to, like, if you don't know answer, it's not possible to guess it. What we need to do, we need to write this state as a superposition of simple computational states, and then calculate what's going on for each of the parts in the superposition. So plus is 0 plus 1. Okay, with normalization, I will write here normalization, so 0, 0. So this qubit is always in 0 state, but this one in superposition of 0 and 1. Okay, now I apply C0 gate. This is control qubit, this is target qubit. What happens to this part of superposition? Control qubit is 0, so nothing happens. So 1 over square root 0, 0. What happens to this part of superposition? So here control qubit is 1, so target qubit flips. So I have 1 over square root of 2, 1. As the state we obtain after application of this circuit. 0, 0 plus 1, 1. How do we call such state? Bell state, more precisely Bell state phi plus, because there are 4 different Bell states. So this is Bell state phi plus. And this combination is combination which very often appears in quantum computing or anything that works with qubit. Because this is, informally, this is Bell gate. Hadamard gate, control X, where Hadamard gate stays on the control line. This is the way how we generate Bell states. So this gate generates Bell states phi plus. If we start from 0, if we start from something else, it will generate another Bell state, or we can rotate this Bell state afterwards, applying gates here. But this is the basic combination which you can find like literally everywhere that builds Bell states, that builds entangled state. If we flip these 2 gates, so we have control not and then Hadamard gate. So this is inverse to Bell gate. This is how we do Bell measurements. If we have a Bell state and but don't know which Bell state, how we can measure this, how we can find out which Bell state we have. So this combination is very like you take any work that does something with qubit. Like I would say more than 50% of works will have gates like this, or inverse, which is Bell state measurement. So this is something like Hadamard gate, and this, like if you cannot, and a result of this gate is much more difficult to calculate than gate like this. Okay, so if you see Hadamard gate and C naught, and you cannot immediately say what is the output is, that, well, most certainly this is Bell gate, and most certainly like you will get Bell state as a result. Okay. Okay, so these were some very simple circuits example. Now let's consider some useful or I would not say useful. Hadamard gate Bell gate is very useful. It's very useful gate. But some simple circuits with C0 that often appear in quantum circuits. Like, let's consider this very simple circuit. So I have 2 C0 gates, one after another. What does this qubit do? Yes, it does nothing. Like if this qubit is 0, well, then it does nothing at all. If this qubit is 1, it applies one X gate, it applies another X gate. Because this qubit stays 1. So we have 1 here, we apply X gate, we apply another gate. So in both cases, well, the end result is nothing. So this qubit, well, it stays, and so we can analyze what's going on if here is 0, then nothing's going on. What's going on if here is 1? Nothing's going on. So we analyze 2 possibilities, then the question, what happens if here I have superposition of 0 and 1? Well, if in both cases nothing happens, if in both cases we have identity gate, like this circuit is equivalent to identity gate, then the same would happen if we have superposition. So, but with superposition, it's actually like it's, if you consider what's going on, like step by step, it's a little bit more interesting. Because suppose this qubit A is in state plus. So I have state plus is a superposition of 0 and 1. So I have superposition of 2 states. Now, I apply this gate. So I have this superposition of this state. Then I apply this CNOT gate. This part, well, it stays 0, 0 after first CNOT gate. Then after second CNOT gate, well, it stays 0, 0. But this part, it takes another route. Here I have 1, 1. After first CNOT. After second CNOT, I have 0, 1. So we have kind of like this state, which is like, this state is not entangled state, because target qubit is here is in state 0. So it's separate. But here we generate entanglement in the middle, and then, well, with these two passes again come together. So it's like interference of these passes, well, but at the end it still produces the same output. So such gates which are, well, which when applied twice, they produce identity gates, they are actually very common in quantum computing because they are easy to think about, and they are called involutions. So involutions is a gate that, which applied twice gives identity gates. So they are very convenient to work with because they are their own inverse. For example, in the Bell gate, when we consider Bell gate, this is involution, this is involution. So if I want to build Bell measurement, which is adjoint or inverse to this gate, I don't need to think about what is the adjoint of CNOT or adjoint of Hadamard gate. Both of them are involutions, so I simply change their order. That's all. So S gate, for example, which is rotation by 90 degrees, is not involution because 2 S rotations gives Z rotation by 180 degrees. Okay, so this is what happens when we have 2 CNOTs in a row. What happens when we have 3 CNOTs in a row? And when we have 3 CNOTs, well, the only way we can arrange them is like this. One goes down, up, down. Because if 2 CNOTs stays in the same direction, this is immediately, we can say this is identity gate. And we can remove them from our circuit. So if I want to put 3 CNOTs in a row, the only non-trivial configurations is like this. So what will be the result of this gate when we, so what does this gate do? And this is already is a little bit complicated because there are 3 gates. So there is a nice method how we can do this type of calculation. So it works when we have X gate and control X gate, so different versions of control X gate. And this method is used on this analytical formula. So if we have C0 of control and target gates, nothing happens to the control gate. Target gate is replaced by target XOR, so this is XOR addition modulo 2 operation. So target XOR control gate. So this is analytical formula. The main advantage of using formula is when you write formula, you analyze all possible cases at the same time. So you have here like 2 qubits. If you want to consider what happens if we have 0, 0, 0, 1, there are 4 different cases, 4 different initial cases. So you have to analyze 4 cases. With this formula, you analyze everything at once. And in your homework, there is example with 3 qubits. So if you want to analyze case by case, there will be 8 cases. Formula, well, is just one case for everything. So let us use this formula. Okay. So I have initially state BA. So BA is a 0 or 1, so they can be arbitrary. So I have state BA. Then I apply first CNOT. For the first CNOT, this qubit is control. This is target. So I replace target with target XOR control. So here I will have B XOR A, A. That's the formula after the first synod. Then this is second synod. Second synod stays in opposite direction. So for the second synod, this is target qubit and this is control qubit. So control qubit stays the same, B XOR A. Target qubit is replaced with target XOR whatever I have here in the control qubit, B XOR A. Now XOR is very nice operation because it's associative, commutative, so it does matter in which order we put, so I can remove this parenthesis. And it also has very nice property that if I take XOR with the same number twice, well, it's the same as doing nothing because it's addition modulo 2. If you add 0 plus 0, you get 0. If you add 1 plus 1, you get 2. Modulo 2 is the same as 0. So here I have A XOR B XOR A. So this is the same as just B. Okay, so this is after the second XOR. Finally, I have third XOR gate. And for the third XOR gate, okay, this qubit is control, this is target. So target is replaced by whatever I have plus control or XOR control. Control stays the same. And here you see we have the same combination, B XOR A XOR B. So B and B cancels and the result is AB.
So you are replacing.
Yep. We started with BA, we ended with AB. So A and B switched. So this qubit is just, this circuit is just switches A and B. And it works, we analyze like all 4 possible computational states in one run here. So this switching happens for every computational state. That will mean it also happens if we have superposition of the states. So this circuit, it performs switching of 2 qubit states, no matter what the states are. So it can be, well, it can be superposition of the states. These qubits may be entangled with some other qubits. It doesn't matter. With this circuit, we kind of flip the identities completely. So this combination, of course, such possibility of switching qubits is useful for, especially when we consider real quantum computers with exact topology, when each qubit has its physical place. Possibility to switch nearby qubits is something which is necessary for quantum programs to run. So this is very useful. And it's called swap because it swaps qubits and it has its own special notation like this. So line with this axis, so we started with AB, we ended with BA. So this is very useful qubit and it's achieved just with 3 CNOT gates. Okay, so let's consider a few more examples. So now, next we will consider some sandwiches. And what is sandwich? Sandwich is when a gate is between two other identical gates or gate and it's adjoined. So let's consider this case. So here I have C0 and I have X and X. So this is sandwich. So X here is only on the control qubit. What does this circuit do? Well, we can, like as always with sandwiches, we can use argument about change of basis. So what sandwich does? Some gate, another gate, first gate adjoint. Like for X gate, X is its own adjoint. So basically here we have kind of change of basis. So when we have sandwich, the easiest way to understand what this sandwich does is to consider change of coordinates produced by this basis. So this gate, it applies X when here is 0. Oh, when here is 1. right? So control. But X gate, it changes 0 and 1s. So this circuit will apply X to the target qubit when input qubit is 0. Because this sandwich, it flips role of 0 and 1s. Okay, so let's see. So if here is 0, I apply X gate, I get 1. I apply NOT gate to the target qubit. And here I have 1, and I apply X gate again, so I end up with 0. Started with 0, ended with 0. The effect is application of X gate. If here I have 1, apply X gate 0, okay. I do not do anything to the target qubit. Apply X again, 0 becomes 1 again. So this sandwich, it changes control condition for C0 gate. So this particular change, well, so this particular configuration creates so-called anti-control gate. So control gate, it applies gate to the target qubit when control condition is 1. Anti-control gate, it applies this gate when condition at this point, like, because if we consider this as a single gate, so when input value of the control qubit is 0. So there is even a special notation for this. So this anti-control gate often is notated with hollow circle. Well, it's not 100% standard notation, but it appears in research papers. It's like there is possibility to create such gates in some quantum simulators and like that. But what is more important is that this sandwich, it illustrates how we can change control condition. We have control NOT gate, which applies not only based on position of a qubit, like along the direction. So this control NOT gate, it distinguishes between 0 and 1 state of the control qubit. Sometimes we want to use different conditions. We want to say activate qubit when we want to apply gate when say qubit in state plus or minus. So how to do it? Well, we should use sandwich along the control line. Well, and so on. Okay, one more thing. So this will be H sandwich, so Hadamard sandwich. But this time I have Hadamard sandwich on the target qubit. So, but it is still sandwich. So what this qubit, what this circuit do? We can use the same thinking about like usually with usual sandwiches. So first of all, let's see what happens if control qubit is 0. So if control qubit is 0, so there is no gate X at this point. I have simply Hadamard gate, Hadamard gate. 2 Hadamard gates in a row is the same as identity gate. So when control qubit is 0, so this circuit does nothing. So this is a type of control gate. Control gate is the gate that does something like general control gate, not just control NOT gate. Control gate is a gate that does something to target qubit only when control qubit is 1. Okay, so now let's consider what this action on the target qubit will be. So what happens if here I have state 1, if control qubit is 1? If control qubit is 1, I have Hadamard gate, X gate, Hadamard gate. So this is a standard sandwich that describes transformation of coordinates. That describes like X gate applied in different coordinate system. So X gate, it's rotated by 180 degree about X axis. Hadamard gates maps X axis to Z axis. So what this gate does, it applies 180 degree rotation, but about Z axis. Control version of it. When you worked with a single qubits like you and In some of the homework problems, you even show this formula for the problem with broken quantum computer. So how to implement Z gate if we don't have it? And you wrote Hadamard gate, X gate, Hadamard gate. This is not the only possibility, but this is some of possibilities some of you wrote. Hadamard gate, X, Hadamard gate. Now the question, how to realize controlled version of the same gate. So this is how we can realize it. We apply control to X. We do not need to apply controls to Hadamard gate, because this is just transformation of coordinates. If I don't have anything here, if here is like blank space identity operator, this transformation of coordinate back and forth does nothing. So I need to apply control conditions only here. Okay, so this gate, this is a control Z gate. Okay, and it has its own notation. So in Kirk it is realized, it is denoted like this. Control and Z, because it's control Z gate. In Qiskit, it has a little bit more interesting notation like this. And this notation, it's symmetric. So where is control and where is target here? So why we are using such symmetric notation? Well, to understand this, let us see what control Z gate does in computational basis. Let's just write like a formula for this gate, similar to what we did with control NOT gate. So control Z gate, it applies Z gate to target qubit if control qubit is 1. So this is this version of control Z gate. So this is control qubit. If it's 0, then nothing happens. Control qubit is 0, nothing happens. So here control qubit is 1, but so this circuit will apply Z gate to target qubit. But target qubit is in 0 state. What happens to qubit if we apply Z gate to such state? Nothing. 0 state 0. So this state also does not change with control Z gate. The last state. So control qubit is 1. So we apply Z gate to this qubit. What happens to state 1 when we apply Z gate? Well, it changes phase. It changes phase. So here's a phase change. And now look at this like truth table for this gate. Nothing happens in these three cases, but phase of one state changes. And this truth table is symmetric. So because we change phase only for the state in which two qubits are 1, 1. So therefore, for such control Z gate, it does matter whether we have control here or control there. And we can use symmetric notation for this. And this is like very unusual, because control X gate is very asymmetric. We have control qubit, and there is nothing happens to it. And we have target qubit, which we actively change. But using this non-classical quantum Hadamard gates, we turn this gate into completely symmetrical one, in which difference between control and target qubit does not exist. So this CZ gate is the only 2-qubit gate which is implemented on hardware level with modern IBM quantum computers. So these quantum computers on which you do your homework, so they support this control Z gate as a native operations. So previous versions of IBM quantum computers used control NOT gate. That was like their gate. But with new versions of control Z is implemented. Well, control Z is symmetric, and I suppose it leads to smaller errors and so on. And this is the only 2-qubit gate that quantum computers, IBM quantum computers have. They in general have not a lot of gates. So we have control Z. Okay, this is identity. So this is just delay. We can measure, we can reset. Okay, if else is a conditional application, if some classical bit is 0, 1, we can apply some other gates, so this is different. So these are single qubit gates, really single qubit gates. Arbitrary rotation about z, and we already know that this arbitrary rotation z is just a delay. Square root of x, and x, which is 2 square root of x in a row. That's all. So we have 1 2-qubit gate. Well, this is virtual gate, so we will not count it, and square root of x. And that's enough. So just a 2 elementary operation, but well, classical computers, well, they also don't have a lot of operation. All classical computations can be done with 1 NAND or NOR gate, and that's all. So 2 is enough. Okay. Yes.
This is why in the lab, if I sort of do with Qiskit, my kind of nice circuit, and I understand everything, and then I give it over to the actual quantum computer, and I don't understand, and it just looks.
And it looks like a mess.
Yeah.
Yeah, a lot of gates. Yes, this is because during this transpiling stage, your nice code with the gates that we understand is compiled into something that can be realized with a particular computer. And there is usually much more gates because we need to combine this elementary operation, and it looks like a mess, and it's difficult to understand. So you can just look at it, but well, analyzing it is a completely different story. Yeah, so that's why. Well, the same happens with classical programs. You write program with something like Python, then well, Python doesn't compile, but it does matter. So you write it in a nice programming language, then you compile it to machine code and look at machine code. There will be much more constructs than in programming languages, and it will be much more difficult to understand. So here with quantum computers, we have very similar situation to quantum. It's just like these operations are not just machine codes that we have, or machine operators that we have, say, in assembly language. These are even much deeper. It's like my codes of microprocessors that exist. So it's like the lowest level of physical gates. Okay, so one more example. So here is a double H sandwich with C naught. So we have C naught, and we put it in H sandwich both with control and target. So let's see what this simple circuit does. And this is really interesting. When I first saw this and saw what it does, like writing formula, I thought I made some mistake. Okay, because it's an interesting result. So first of all, I can rewrite like this circuit. I can move this to gate a little bit further away because it does matter. And what I have here, I have here like single H sandwich that we just considered. And this is control Z gate. We know that this is control Z gate, so I can replace it with control Z gate. But control Z gate is symmetric. So it does matter whether I put control and where I put Z. So I can flip it, right? I can flip it like this. Okay, now that I flip it, I will expand it as H sandwich again. So I expand it as, instead of control Z, I write it control naught and 2 Hadamard gates. So this is what we have. So this is equivalent circuit. And now see, like here I have 2 Hadamard gates in a row. So they do nothing, so I can remove them. And what remains? Remains only this C naught gate. And what is most amazing is that here I have C naught gate as controlled, which is directed upwards, and here I have C naught gate in opposite direction. So I have C naught gate in which I have one control qubit, and nothing happens to it. Control qubit, it stays the same as it was, and something happens only to the target qubit. This is what our classical understanding tells us. Then I put this gate in a sandwich, Hadamard sandwich, and it flips its direction. Now nothing happens to this qubit. And all the action is in the qubit that was previously controlled. And this is really like this is something that, well, when I first saw this was very amazing, like how we can do this. And this fact actually was used like in like first version of IBM computers. So when there was 2 qubits which are connected, there was one-way connection. You can apply C0 gate only, say, like when this qubit is controlling this target. Because this direction is defined by how you build microwave resonators about this qubit. So you encode this direction of C0 in hardware. Okay, and if it would not be possible to reverse direction of C0, such computers would be very, very useless, basically, because we can apply C0 only. First of all, we have practically linear configuration of qubits, and if we can apply C0 only in this direction, there is not a lot of circuits we can do. But this is not a limitation. Well, right now we have CZ gate, but this one direction of C0 was not a limitation, because what is important is that 2 qubits can interact. And then using some single qubit tricks, we can put direction of C0 as we want, or we can turn C0 into other control operation. Okay, so this is very interesting fact. So in quantum world, there is no such thing as one qubit acting on another and staying the same, because every interaction is interaction. 2 things interact. So when we have C0, the control qubit does not change only if we consider states in computational basis. If we write action of C0 in a different basis, it will have different form. Okay, so what this sandwich is, basically we rewrite this C0 in a different in a different basis. So in quantum physics, it always works like that. It's not possible for you to interact on something and not being changed. Every interaction changes both paths. Okay, so let's move on. So we saw that we can create many circuits with C0. We can swap qubits, we can apply Control Z, and so on. So the question is, what is the maximum set of gates that C0 allows, or circuits or programs that C0 allows us to build? And the answer is that, well, we can build any multi-qubit gate, absolutely any. We can write absolutely any quantum program if we have this C0 gate and 1 qubit gates. So this C0 and 1 qubit gates, that forms of called universal set of gates. Set of gates that allows us to build absolutely anything. Well, in fact, this is not that, well, interesting, because as I said, classical computers can build everything with just 1 gate, which is a NAND or NOR. So like this. So here, well, it's like that. Yes.
Is that also double state with this? Or
yes. Well, Hadamard is 1 qubit gate. So we need C0 and Hadamard gate. Yes. So informally, what we need from set of gates to be universal, we need single qubit operations. And we need operations that produce superposition of 0 and 1s. Because we always start from 0, so we need some way to create superposition. This is done by Hadamard gate. We need some gates that produce complex amplitudes. We usually consider 0, 1, plus and minus, they are real, but this is not like universal set of amplitudes. There are like I, minus I, and basically to get to any point on Bloch sphere, we need some complex amplitude. So we need a special gate with complex numbers to produce complex amplitude. For that, we can use either S and T. And we need some gates that will allow us to move from these 6 special states along coordinate axis. This is rotation by angle less than 90 degrees, which can be T-gate rotation by 45 degrees. So if you have single qubit gates that satisfy this 3 property, you can combine them to build any single qubit rotation you want. So in reality, we need Hadamard gate or something like that, and like rotation about the axis. So this is a single qubit rotation.
So,
Yes, go on.
on the previous slide, the single gate, it means
One
the
qubit.
one which turns just 90 degrees. So you need more or less universe of single
Yes,
gate.
yes, yes.
You can do
So
everything.
we need to have like, we need to be able to do with single qubit whatever we want. Yeah. But it's not that difficult, as I say. Like in reality, we need some gates that produce superposition, Hadamard gate, and some gates that rotates by arbitrary angle. So in quantum computers, this rotation, it's a virtual rotation about the axis. We can simply like change like the time stamp. And instead of Hadamard gate, it's easier to realize square root of x. Well, square root of x is like you start from this, you end up at that. So it's just technically easier to realize. So this is what we need from single qubit gates. And then we can combine them to do whatever we want. And we need some means to produce entanglement, which is CNOT. So basically, like if you can do everything with a single qubit and you know how to produce entanglement, you have universal set of gates. And modern quantum computers, they can do with single qubit whatever you want. Like, okay, using virtual gates and some combination of basic gates, but with single qubit, it's not a problem to rotate it as you want, and it's fast and reliable. With single qubit gates are much more difficult to realize because you need to have 2 qubits that will interact, and this interaction, well, it should be such that, well, you do not break any entanglement, you do not introduce any decoherence and so on. So multi-qubit gates are much more difficult than single qubit one. And whatever model of quantum computer you take, there are several like approaches. There are many companies making that. Usually there is just one type of 2 qubit gates. It's only one 2 qubit gate. Okay, so as I said, IBM right now uses Control-Z, previously used CNOT, but this is enough. This is enough, so do it. Okay, let's consider some other control gates. So in principle, if we have any single qubit gate U, so it can be whatever gate, we can create controlled version of this gate using like a simple rules. So when this control qubit is 0, we do nothing. When this qubit is 1, well, then we apply this gate U, which can be whatever gate we want. We apply this gate U to the target qubit. So such gate, like in analytic in formula, they denote CU. Control U, similar to CX, control X, or CZ, control Z. So, and this creating control version of a gate is like a standard ways how we introduce new gates, how we build some composite gates from existing ones. So like all simulators and even Qiskit can like write how to realize this gate using like standard control node and other gates. So when we have such control gates, it's very easy to write it in matrix form. Well, it has very similar forms to control nodes. So it's block diagonal. This block describes what happens when control qubit is 0 and there is nothing happens. So here I have identity matrix. This block describes what happens when control qubit is 1. And this is basically this matrix of this single qubit gate. So for control node, I would have here 0, 0, 1, 1, like X gate. So in block form, this matrix of control gate has this nice shape, diagonal matrix with identity new gates. And so you can immediately write this matrix form of control gate for any control gate. And actually this also works even if this U gate is not single qubit gate, but say gate that acts on several qubits. So you can immediately write this matrix form. So this is such control gates are very convenient to simulate because we have matrix form. Okay, how can we build this control U gate if we are limited to single qubit gates and control node? Well, that depends if this gate U, this single qubit gate U, what type of rotation it describes. So suppose this gate U describes rotation by 100 degrees about some axis. So we know how to realize control version of rotation about x-axis. Well, now we know how to realize control rotation about z-axis, but suppose we want to realize control rotation by 180 degrees about some arbitrary axis. So if U is such 180 degree rotation, so it can always be written in such sandwich form. So G here is the transformation that maps x coordinates, so this is x coordinate to this axis of rotation. So what this form does, it tells like we need to read from right to left. It says take this axis of rotation, put it into x direction, then rotate about x-axis by 100 degrees, and then put this axis back. So this formula is a sandwich form for rotation about this axis. And once you write gate in such sandwich form, you can immediately write its controlled version. So how to realize this control U gate? Very simple, like this. This is exactly the form which we considered a few minutes ago for control Z gate. For control Z gate, this map between x and rotation axis is just a Hadamard gate. But in general case, we can write this. And this is something that can be easily calculated by people. Okay, so this is the full control X form. Now, its situation is more complicated when this gate that we want to realize is rotation by some small angle, not 180 degree, but something, say 90 degree or some arbitrary degree. So in this case, we cannot write it like in simple form, but we always can decompose it like this. So what this formula means, here I have two sandwiches. One sandwich is rotation by 180 degrees defined by axis A, another is defined by axis B. So, and whatever rotation we have, we can always decompose it as rotation about some axis by 180 degrees and then about another axis. It's not that easy to find this rotation axis in this case. So probably here you need some help of computers, because by hand it's often quite difficult. But this can be done always. And this is the decomposition. So if here we have 0, I have I plus I, which is identity, B plus B, which is identity. So it does nothing. If control qubit is 1, I have one rotation about axis A, I have rotation about axis B, and this is my desired gate. Sometimes it's possible, it's much easier to find, to realize this decomposition, we need to find A and B that satisfies this formula. And sometimes it is easier to find like A and B which are equivalent to U up to a global phase. So we can find such A and B that produce U, but introduce a different global phase. And here is important thing. So if I had just the gate U, then it does matter if I use U or U with a global phase. It's the same thing. But it's not the same thing if I have controlled version of U. Because in controlled version of U, if here is 0, this global phase will not be added because, well, nothing happens in this case. But if here is 1, if control qubit is 1, we will add this additional phase. So for control version of gate, global phase becomes relative phase. So this is when you need to pay attention. So, and if we, but this phase can be simply compensated by additional phase gate on a control qubit. So such decomposition is something that you can actually often see, say, in textbooks or papers on quantum computing. Okay, so these are basically like 2-qubit gates. We can build all 2-qubit gates just from CNOT, and it's clear how to do this. And 2-qubit gates like CNOT is universal, but often if we want to write a program, we need some gates that work on more than 2 qubits. They also can be built from CNOT, but it's more convenient to have them ready. So one important gate is so-called Toffoli gate, or control X gate. So this is how it is denoted, and like you can understand what it does simply from this so from this picture. It applies X gate to target qubit when here is 1 and here is 1. So this is a gate that has 2 control qubit and apply X gate to target qubit if both of these qubits or both of controls are 1. So in Qiskit it's called CCX. You can use formula to describe this. And in contrast with 1CX, well, as 1CX we do not have here like Q2, we have Q0 XOR Q1. So we have single control X can allow us, it allows us to realize operation of XOR, logical operation of XOR. It is built on in formula for control NOT. But XOR operation is not a universal logical operation. For example, if we just have XOR function, you cannot build you cannot build AND function like in usual classical Boolean algebra. So Toffoli gate like introduces this product of qubit, Q1 and Q2, and product is the same as AND operation. And if we have XOR and if we have AND, we can realize absolutely any logical function. So if we want to build some logical circuit that resemble classical circuit, it's Toffoli gate is very useful. Okay, for example, like using Toffoli gate, we can realize AND function. It's very easy. So if here is 0, then output is just AND of 2 control qubits. It's by definition. Using classical Boolean laws, we can turn this AND into OR. So basically, we can realize absolutely any logical operation. Okay, so here, how we can build this Toffoli gate or control X gate from single qubit CNOT gates. You see, it's a very complicated decomposition, but it follows the same ideas as usual, like decomposition that we see. So let's say here you see, here is a sandwich. We have gate, we have a joint of this gate. Here is another sandwich. If you look what this does, HH, there is another sandwich. So these are rotations about different axes just combined in a proper way such that will give the CCX. But this is really difficult. And like since real computers, they can realize only C0 on CX, so such gates, they're useful, but they're expensive in terms of number of gates that we have. Okay, that is all about like main part of this course. I have also in this lecture slides for you later to see how to build majority gate. So majority gate is one of classical gates. So majority gates, it produces here one, when so it has 3 inputs and 1 output. So majority gate produces here one when at least 2 qubits, no matter which 2 qubits, are in state 1. So how to build majority gates in quantum computing? So first of all, we cannot build gate like this because it is irreversible gate. So it has 3 inputs, it has 1 output. But there is standard way how we can turn irreversible classical gate into reversible gates that can be realized in a quantum computer. So this is reversible version. It has 3 inputs and it leaves these inputs as output without any changes. And it has one more input which is called ancilla. And what this gate does, it simply XORs this ancilla, initial state of ancilla, with classical majority function. So, and this gate is reversible. So gate like this is always reversible because these qubits, they stay the same. And ancilla qubit is simply XORed with the result of any calculation. So if you put 2 of these majority gates together, what will happen? Ancilla gate will be XORed once with this function, it will be XORed second time with this function, so ancilla will return to itself. So this formulation of majority gate is involution. You apply it twice, well, you get identity gate. Okay, so this version can be realized. And to do this, like, the useful thing is to write this classical function using XOR, which is realized either with CX or with control not or control not, and function. And for n function, we need Toffoli gate, control X gate. So majority function, logical function, can be written as this form. And you see, so here to get this product, we need to apply control X gate, because in control X, we have exactly this combination. So you can read more details about this later in slides. I just will show you results. So here is this circuit. So here I realize arbitrary Boolean numbers. So these are 3 random choices. Hadamard gate measurements. So here I will have absolutely random combination of 0 and 1s. This is the way how I will check all input at once. And here is this 3 control not gates, so which correspond to 3 this time. Okay. So this is how nice this majority gate, and the last qubit is this output qubit. So this is a very nice form for majority gate in terms of Toffoli gate. This is how it looks like when you transpile it in real quantum computer. So there are a lot of gates, so there are several lines of it. Why is it happens? Because here I have 3 Toffoli gate, and each Toffoli gate is expanded in something like 6 control not gates. So I have a lot of these control not gates with some rotation in between them. So this is very long program, very long program. Okay, so these are results. Blue are correct results, orange are when it's wrong. See, it works quite good, but still error is about 10%. So we can realize such gates on a quantum computer. It's clear that they work. But like if the question is to build a pipe of say 5 or 10 of such gates, then this error will compound, and well, we will not be able to do this simulation. But say 5 years ago, like trying to build gate like that would lead to such large errors that you practically will not see here any effect. So right now,
5 years ago.
Huh?
5 years ago.
Yeah. It's about 5 years ago when I first started using quantum computers, and they were much more difficult to work with than right now. Yeah, so the progress in 5 years is very significant. And like 5 years ago, you have to really like choose like what you do. Like say this program, I would not write program like this 5 years ago. I would write 8 different programs for different inputs. Because here I have Hadamard gate plus measurement. So this is like additional like load on this program. So there are errors also during this stage. And 5 years ago, I would say, well, this increases, well, large errors that I have, so I will build like a special circuit, 8 different circuits for 8 different inputs. Right now, I can do things like that and still see the effects clear. Okay, that will be all for today. Any questions? Yes?
With the quantum computer, is it dependent on which quantum physics are used to actually realize my qubits? Is this dependent on which gates are easier or harder to build?
Yes, for different realization of qubits, there are different sets of gates which are easier to implement. And so again, like there are like qubits in superconducting qubits that IBM uses qubits based on trapped ions or atoms, photonic qubits with photonic computers, well, but they use slightly different approach like in general. So, but for different realization of qubits, there are different sets of gates. These sets of gates, they are all universal. So like theoretically, you can do whatever you want with any of them, but they introduce like different errors and so on. Right now, it is still too early to say which realization of qubits will be dominant. Like, so I'd say we still don't have transistor. Like with classical electronics, we have transistor, and we do everything with transistor. Even resistors are now built with transistors. Okay, so transistor like replaced everything else, basically, any other element that existed before. But in quantum computer, we are still far from that. There are several different models, like more than 10 realization of qubits, and people study them and people try to advance particular this, but still there is competition, and who knows what will happen in 5 years. Any other questions? Yes?
How can we make majority gate in magnonics?
Oh, that's a very good question. So if well, for majority gates or similar gates, well, we need to realize something like this. So we need to have something like a Toffoli gate. And this gate, like you see, here is a product of two states. And product means nonlinearity in magnonics. Product because just plus, this is what we have for control nodes. This is something that I think can be easily done with magnonic, because plus or XOR is a linear operation. This is a product. This is nonlinear operation. So we need to introduce nonlinearity to magnons. Magnons are nonlinear when we are talking about classical electronics, when we have more than one magnon. But when we have just one magnon, so to realize quantum, like quantum majority gate, we need somehow to increase this nonlinearity of magnons. This is either to go to some very small magnetic element, like if we have ferromagnetic sphere of some 10 nanometer diameter, well, then it will have enough nonlinearity such that we can realize things like that. Or we can use some nonlinearity based on say interaction between magnon and qubit. So maybe to realize gates like that, we should not consider just magnons. We can consider we can have something like a ferromagnetic sphere, and we can have qubit nearby, and we can consider this as a particular, like as some dressed qubit. This dressed qubit will have properties similar to properties of usual qubit, so it will have nonlinearity, but it also will have properties similar to magnon, so it can, say, interact with of phonons. It can easily interact with electromagnetic waves, even with optical waves and so on. It can be parametrically driven to create some special state and so on. So maybe this is approach. It's in quantum magnonics we are at the very early stages of it. So no one realizes yet. So you should try to do this. Okay. Other questions? Okay, well, that will be all for today.